Hello, AP Chemistry. We are looking at Unit 5 today, kinetics. I'm not sure if this video will be the entire unit in one shot or if it will be broken into multiple parts. So definitely check the title of the video because I don't know yet as I begin. So uh, looking at our slides for the unit. All right, Unit 5, kinetics. So some reactions happen quickly while others happen more slowly and depend on reactant concentrations and temperature. All right, so when we say kinetics, we're talking about the rate of a reaction. And rate, especially for anyone that's taken physics, rate, it's the rate of change. So it's the change in concentration over the change in time. All right, so what we have in this graph, the kinetics of a chemical reaction is defined as the rate at which an amount of reactants is converted to products per unit of time. The purple is representing the reactants, and we start out with a lot of them, a high concentration, and as the reaction proceeds, it declines, right, to a point where we eventually have no reactants left. Now, the products, they start out at 0. We don't have any of the green initially. We make a lot, and then it moves on, all right? Two things I really want to point out here. One, a majority of the change happens right out the gate, all right? So we get the most change in probably those first 10 seconds, first 20 seconds, and then it starts tapering off. And we will also see that the reactants will always decrease, the products will always increase, all right? And that should make sense. That should be fairly logical for us. We start without any products, we start with all reactants, we lose the reactants, we make the products, all right? Now, what we're gonna be looking at, all right, it's tangent lines, all right? So we're looking at instantaneous rates. So that is something that comes up in calculus, all right? But we're looking at kind of a tangent line to any given spot, and we're trying to figure out what the change in concentration over the change in time is, all right? And we will also specifically, we really only care about the rate that the reactants are lost. We don't look at the rate that the products are formed as much, although that might be part of an experimental design. All right, so the rates of change of reactant and product concentrations are determined by the stoichiometry in the balanced equation. All right, so if we have our balanced equation, all the lowercase letters are representing the coefficients. The rate for any reactant has that negative sign, all right? Because keep in mind, we lose reactant. So those rates are all going to be negative, right? Because it's downward sloping. But what we put in front, so the change in concentration over time, we set up a fraction, 1 over the coefficient. So if these were all 1s, this would be simple, 1 over 1, 1 over 1, 1 over 1, 1 over 1, if lowercase a, b, c, and d were 1. But let's say you had 2 in front of one of the reactants. It would be 1/2 times the concentration. And again, this is a way to kind of set each piece equal to each other. And we just want to think with that stoichiometry, if it was like a 1+3 ratio, right? You needed 1 of reactant A for every 3 of reactant B. Well, you're going to lose more reactant B because you're going to use 3 of them for every essentially round of the reaction. So that's where this comes from. This is not an equation that we use very often, though. All right, it's just kind of setting it up so we know that if those coefficients are there, they do matter, and it kind of tells us how quickly we may lose any given reactant or how quickly we may make a product. All right, and just as an example, here's 2NO plus O2 forming 2NO. All right, now what they are doing is, from the previous slide, instead of the concentration A over concentration, delta concentration of A over delta T, they're just switching it to the rate of A over its coefficients. So for NO, it would be over 2, and it's negative because it's a reactant. For O2, it's over -1. And for the NO2 that we're forming as a product, it's divided by 2. But this is how we can kind of compare their rates, all right? So now the rate of a reaction is influenced by reactant concentrations, temperature, surface area, catalysts, and other environmental factors. All right, this is the really simple explanation of how we get faster chemical reactions. All right, temperature increases the rate of a reaction. All right, because it gives the individual reactants more energy, so they're easier to reach that activation energy. They're able to have more collisions. That's getting into the theories behind a reaction. Um, the concentration allows for more collisions to happen. The catalyst, all right, it provides an alternate pathway, and we'll see the catalyst in its own big thing. And the surface area, we also call that the ability to meet. But the surface area, the reactants need to be in contact with one another. So if we had, let's say, something like iron metal reacting with hydrochloric acid, if we grind up that iron metal, it's going to be able to meet the hydrochloric acid molecules in solution much easier. All right, now, if we use a large chunk of iron, it's only going to be able to react on the surface. So all of those inner iron atoms won't be able to react until everything in front of them has reacted. So surface area factor in how quickly a chemical reaction will take place. All right, now, experimental methods can be used to monitor the amounts of reactants and or products of a reaction and to determine the rate of the reaction. So um, setting up kinetics experiments is something that is pretty difficult. All right, so typically in the questions we look at, right, in the theoretical questions we look at, we are always looking at the rate of reaction of the reactants being used, but that's not something that's easy to measure. So here's an example of a reaction. This could be an experimental setup, a reaction where the reactants produce a gas. And what we're going to do is the gas is going to be collected and it's going to be connected to a gas syringe. So as more gas is produced, the syringe will expand against a constant external pressure, right? So as we make more gas, this will expand. Think of it almost as like a balloon. If you had more gas on a balloon above a flask, it'll get bigger and bigger and bigger. So as the syringe expands, you have an idea of how much gas you've made. So now here you would be looking at the rate of gas being produced, and you can measure it versus time at the stopwatch. All right. Another example would just be a reaction with a pretty dramatic change, and you would use a stopwatch. That would be something like the iodine clock reaction. All right? I know I've done the iodine clock reaction several times in the past. I'm not sure if we got to it this year. Several YouTube videos on it. It's a reaction where a solution goes from clear to black very instantly. All right, so there's a reaction occurring, and once it runs out, essentially, the reaction is preventing that black color from appearing. Once that reaction can't go anymore, the solution just turns black, and that's something you can do at different concentrations. You can use a stopwatch, and you can record it. All right, so that would be an example. Here's another type of lab where the solution goes from clear to almost like milky, and you can do it in a flask over an X, and the X will disappear. All right, so again, you can keep a stopwatch in hand and measure it for different temperatures of the solutions or for different concentrations of the solutions, things like that. So that is a way that you can set up some of these experiments. The last one is a reaction that changes a shade of color over time. All right, so we see 1 through 10, the reaction steadily gets darker. All right, you can kind of eyeball this if you wanted to. You can set up standards if you want to look at it against it, but you can also use the Beers-Lambert law, right? So you can measure the amount of light that's going through the solution versus time, right? So the absorption is going to be directly connected to the concentration, so you can get an idea of the concentration of this product that's turning brown. Concentration's low, it's increasing, 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 right? And so if you can get those measurements at each spot, you can come up with a pretty simple graph, concentration versus time, which is looking at the rate of reactions. That is the kinetics. All right, so this leads us to the rate law, right? We don't use from a couple slides back, we don't use that 1 over the stoichiometric coefficient times the rate and setting everything equal to each other. What we like is the rate law. This is like our good one. All right, so the rate law expresses the rate of a reaction as proportional to the concentration of each reactant raised to a power. All right, so the rate of a reaction is going to be equal to K times the concentration of A raised to some power times the concentration of B raised to some power. All variables that are placeholders. All right, we will always have K. These powers, they can be 0, right? So the concentration of a reactant can be raised to the 0th power, which just gives us 1. It could be 1, 2, 3, 4. I mean, it can just keep going. And these could even be fractions, all right? It's not completely unheard of. It's very rare. It's very rare, especially in the AP chemistry curriculum, but it's happened in the past, all right? But everything multiplied together, it equals our rate, which is molarity per second. Here it's being listed as mole, decimeter to the -3rd, second to the -1st. All right, so I would say mole per liter per second, but they want to use this fancy stuff. All right, so the important thing to remember, when we say rate, we are talking about instantaneous rates, and we try to get the earliest possible instantaneous rates because those give us the most dramatic effect, and it gives us the most accurate approximation. As our line, as our reaction proceeds for longer and longer, our instantaneous rate is no longer as good. All right, so when I say rate in the rate law, I am talking specifically about the instantaneous rate. And there are ways to measure that in a better lab. They would have more precise equipment that can detect the presence of certain concentrations of certain elements, certain compounds. All right, so the power of each reactant in the rate law is the order of the reaction with respect to that reactant. The sum of the powers of the reactant concentrations in the rate law is the overall order of the reaction. All right, so in this example, the rate equals K times the concentration of NO raised to the second times the concentration of H2 raised to the first. So we would say this reaction is first order with respect to hydrogen and second order with respect to nitrous oxide. All right, so first order with respect to hydrogen because of the 1, second order with respect to nitrous oxide because of the 2. These are not stoichiometric ratios. All right, that is not where this information is coming from. Now we add up the coefficients, we add up the powers. This reaction is third order overall. All right, and that's all important information for us knowing the order of a reaction. So the proportionality constant in the rate law is called the rate constant. All right, that's K, and that's going to set everything equal. The value of this constant is temperature dependent, and the units reflect the overall order of reaction. All right, so the rate law is always concentration per time. So K is going to kind of provide this function where whatever our units here are, right, and our concentrations are always molarities, and they're being raised to certain powers, neither of them have time. So K is always going to have per second, right, 1 over second, but it's going to connect everything, all right, and K, it's kind of going to explain, even though the powers will explain how changes in concentration change the rate law, K kind of connects it all together, right? K kind of dictates, is it a really fast reaction? Is it a really slow reaction? The individual concentrations just tell us how that piece can affect it. And K is temperature dependent, all right? So if we increase the temperature, K typically will get bigger because the reaction will get faster, all right? So now the units. If the overall reaction is 0 order, all right, because rate is molarity per second, K's units will be molarity per second, and rate will just equal K because any reactants will be raised to the 0 power here. Now, if it is a first order reaction, that means we are already getting the molarity units from the concentration, the first order concentration. So the K units are going to be 1 over seconds. So we'll get molarity times 1 over seconds. Now, if it's second order, the molarity is going to be squared, All right, so we're gonna have molarity squared. We only want one molarity to stick around to equal the left side of the equation, the rate. So we're gonna have to do 1 over molarity so that we get molarity squared over molarity, and one of them cancels out, and we still have the per seconds on the bottom. So for second order, 1 over molarity times second. Third order, it's the same type of scenario. Molarity is being raised to the third power. We want 2 of those powers to go away, so we're going to have to divide by molarity squared on the bottom. All right, just something to keep in mind, the capital M for molarity is moles per liter. So molarity per second could also be written as moles per liter per second. 1 over molarity times second, we can invert the molarity units. It could be liters over moles times second. Same thing for 1 over molarity squared. It could be liters squared per moles squared times second. All right, so take a second here, pause, replay that back if it didn't make sense. But knowing the units from the order of reaction, knowing the units for K is an important piece. It shows up a lot in our free response questions, and I think it's a very fair question, all right, because it's something that you do have to apply a little bit. You have to be a little more comfortable with the units. So I'm pretty certain we are going to see this at some point, and we want to make sure we can handle that. So we want to make sure we can determine the units for K based on the overall order, and the whole point of that is to get the units on this right side of the equation to equal the units of R, which need to be molarity per second. All right, so here in this example, this is a third order reaction. All right, so what units would we want? All right, we're gonna get molarity cubed. So we need to get rid of 2 of those molarities. We're gonna want a molarity squared on the bottom, and it needs to be per second so that when it equals the left side of the equation, it's concentration, it's molarity per second. All right, so now this is a pretty common question we have seen. Comparing initial rates of a reaction is a method to determine the order with respect to each reactant. All right, so what we are given is some data, right? Multiple experiments where the initial concentrations of each reactant are recorded, and the initial rate of the reaction is also determined. So the experimental design here is to try to have multiple trials with the same concentration for any one reactant. So for the Cl2, in experiments 1 and 2, in trials 1 and 2, it's 0.2 molar. So we can compare how the rate changed from trial 1 to trial 2. Since we kept the chlorine at a constant, it'll come down to what happened to the nitrogen. So from trial 1 to trial 2, we went from 1 times 10 to the negative second to 4 times 10 to the negative second. So I would always recommend put the larger rate on top, divide by the smaller one. This one's pretty simple. We can see that the rate has quadrupled from trial 1 to trial 4. It's 4 times faster. Now again, the chlorine stayed constant, so the chlorine did not contribute to that. What happened to the NO? It went from 0.13 to 0.26. It doubled, all right? Doubling the NO caused the rate to quadruple. So what we want to think is, what power does 2 have to get raised to equal 4? If this was a first order reaction, doubling the concentration would double the rate. This is a second order reaction with respect to NO, because doubling the concentration doubled the rate. And then we can use trials 1 and 3 to compare while leaving the NO at a constant 0.13. So we go from 0.2 to 0.1, and that would essentially be halving the concentration, and the rate goes from 1 times 10 to the negative 2 to 5 times 10 to the negative 3. That is being 1 halved. So the concentration is halved, the rate is halved, the order here is 1. All right, whatever happens to the chlorine, the exact same thing happens to the rate. And if there's no change, that's when we get the 0 order. All right, so NO is second order, Cl is first order. All right, Um, Something that I came across, Adrian Dinkel's page. All right, he is a longtime AP chemistry teacher. I have given you some of his links in the past. He put together an answer on writing really good answers. And so in his experiment, like if we're looking at data, we have the concentration of A and B. We see that in trials 1 and 2, A is staying the same. In trials 1 and 3, B is staying the same, and they're giving us the relative rate. Nice, easy numbers, 1, 2, and 4. The way he would set it up, all right, I'm not saying that you have to go this way, but he's a very experienced teacher. He would almost make another chart comparing the trials, listing the concentrations, and then the relative rates and explaining. So so comparing trials 1 and 2, A stays the same, B doubles, the relative rates double. So it's first order with respect to concentration of B, right? Doubled, doubled. In trials 1 and 3, B stayed the same, that's the times 1. A was doubled, the rates were quadrupled. All right, so second order with respect to A. Same information, just something that may be helpful in explaining this information if you are faced with a question where you are coming up with the rate order, all right, where you are using this method of initial rates. All right, and again, we can sometimes get harder questions where we don't get 2 trials that we can keep the same. So we can figure out the rate of A by keeping trials 1 and 2 the same because B is the same. But for determining the rate of B, no 2 trials in A are the same. We would have to manually use the fact that we know whatever that rate is now. So we can get some harder initial rate questions. We can handle those though. So we've seen those, we've practiced those. You may want to look up and do some extra practice on these types of questions, but this is just reminding you the types of questions that we were very successful with in the past. All right, so now the order of a reaction can be inferred from a graph of concentration of reactant versus time. All right, we spent time in class, we saw the integrated rate law. Right, that took the rate law and it integrated it, which is a calculus technique. And I know that not everyone in the class is in calculus, so it's totally fine if you don't know how to do the integration, but we will go through what the conclusions meant because the concentration, the natural log of the concentration, or 1 over the concentration all meant something different for us. All right, so if a reaction is first order with respect to a reactant being monitored, a plot of the natural log of the reactant concentration as a function of time will be linear. All right, so this is the integrated rate law. It's something that's listed in the reference sheet. What I need you to know is if you ever see the natural log of concentration versus time producing a straight line, you know the reaction is first order. All right, we're always looking for the straight line here. So ln of concentration versus time always will happen for a first order reaction. All right, and it will be downward sloping those first order reactions. If a reaction is second order with respect to a reactant being monitored, a plot of the reciprocal of the concentration of that reactant versus time will be linear. So 1 over the concentration will give you the positive slope for any second order reaction. All right. The concentration of the reactant versus time giving you a straight line only occurs for a 0 order reaction. All right, now for second order, again, it's 1 over the concentration. So just recapping, right, we're looking for, if we get a set of data, we want to graph concentration versus time, natural log of A versus time, 1 over A versus time. When you do all 3 of those graphs, 1 of the 3 will produce a straight line. And that's how you know the reaction order. All right. We have seen several free response questions where the prompt gave you all 3 graphs and asked you to pick the reaction order. And then it had follow-up questions with that. But so what you're looking for is the straight line. All right. Now, the slopes matter as well. The slopes of the concentration versus time data for 0th, first, and second order reactions can be used to determine the rate constant. All right, so what's going on is the slope is equal to K. Now, if it's 0 or first order, it's going to be a downward sloping line, so it's going to equal negative K. And if it's for the second order 1/A reaction, that's where the linear line, if it's second order, it'll have a positive slope. So that slope will just equal K. All right, so we see what happens if it's 0 order, K equals negative slope. If it's first order, K equals negative slope. And if it's second order, K just equals the slope. So the slope of that line tells you the K. And again, here's everything kind of summarized in this chart. So if you want to pause here for a second, certainly do that. We have the integrated rate law. And the integrated rate law is something we can use. We've seen this question. We don't do it very often. It can be used to determine the concentration after a given amount of time, right? The regular rate law that we learned helps us determine how quickly the reaction occurs, what the rate will be. But the integrated is the only one that allows us to determine the concentration after a set amount of time. We need to know their characteristic plots, and we want to know what the slope tells us. And the units are summarized again. This is for the rate constant. So for that 0 order, moles per liter per second. For the first order, just per second. And for the second order, liters per moles per second. So it can cancel out. All right, now this does lead us to the concept of half-life. So half-life is a critical parameter for first order reactions because the half-life is constant and related to the rate constant for the reaction by the equation. All right, and the time for the half-life, it equals 0.693 over K. This number, it's not random. It has to do with the natural log of 2. All right, the point of a half-life is after one half-life, half of a sample has reacted. All right, and so this is what it looks like when you have it and you have it again and you have it again and you have it again. But the amount of time it takes to half any sample, it doesn't matter the concentration, is always the same. And again, very important, all half-life reactions are first order, right? So it takes the same amount of time no matter what the concentration is, but the concentration is halved by the end of the half-life. All right, so here we're looking at one that takes about 8 days. So after 8 days, half the sample is reactant. After 16 days, half has reacted. Again, you now have a quarter of it, and then an eighth, and then a half. All right. So the same, so just showing you each half-life, it's the same interval of time, but we lose significantly less in each of them. All right, and here's something interesting we're getting. We are told that the K for this reaction, right, the rate constant, is 0.4. We can do 0.693 divided by 0.4, and it would give us a half-life of 1.73 seconds. All right, so that's what this equation does. The half-life, it's equal to 0.693 divided by K. All right, and K, again, that rate constant, it gives us an idea of how quickly the reaction occurs. The smaller the value of K, the bigger the half-life is going to be. All right, so if we divide by a really small number here, we're going to get a bigger half-life. The bigger K is, the smaller the half-life, right? And again, that's the K, that's the rate constant, right? That's something that does not change for the reaction. And again, only first order reactions. So now, radioactive decay processes provide an important illustration of first order kinetics. Nuclear chemistry is not something that's really on the AP curriculum anymore. It's been taken out. Maybe they'll bring it back. I hope to, before the exam, do a pretty short, hopefully 10 minutes or less video on nuclear decay. I don't want to get into all of it right now, but it's pretty simple. There's 3 types: alpha, beta, and gamma decay. And in all of those types, something gets emitted from the nucleus of an atom, and it changes the identity. So we always go from the parent to the daughter. The gamma, actually, the parent is just an excited state, and the daughter is actually the same. But in alpha decay, we actually change the identity of the element. We may go from uranium to plutonium, something like that. In a beta decay, we're going from something like carbon to nitrogen. They change in a very specific way. Again, we don't have to worry about that, but all radioactive processes are first order reactions, and they all have a given half-life. So what ends up happening is we have a sample of all one element, as it undergoes that radioactive decay, some of those atoms, they're essentially flipping. They are losing something from their nucleus and they're changing from the parent to the daughter isotope. And we see that, right? We get half, then a quarter, then an eighth, and over time we go from all red to all gray in this example. All right, and it comes up a lot. Just we use these radioactive reactions because they're always first order kinetics. All right, now the rate law of an elementary reaction can be inferred from the stoichiometry of the molecules participating in a collision. All right, so an elementary reaction is part of a mechanism. Now, normally for a given reaction, we would never look at the stoichiometry to determine the rate law, but an elementary reaction, it's the subsets or the smaller individual steps as part of a reaction mechanism. So we'll actually stop here and we'll pick up with this slide in part 2.